In the world of AI, we're always told that bigger is better. More data, more parameters, more computing power, you get the idea. But what if that wasn't the whole story? Today, we're going to dig into a really fascinating paper that just flips that idea completely on its head. It shows how a smaller, leaner AI can not only match its giant teacher, but get this, actually outperform it.
I mean, that sounds totally backwards, right? How on earth do you get more intelligence with less? Well, that's the central puzzle we're going to unravel today. And it's a concept that could seriously change how we build and use AI in, well, pretty much everything from our phones to our cars. All right, let's dive in.
So first things first, we've got to understand the problem that researchers were even trying to solve here. Because the biggest, most powerful AI models we have today, they come with a massive catch. Okay, so you've got this real tug of war happening in AI. On one side, you have these state-of-the-art models. I'm talking about the record breakers. They are incredibly accurate, for sure, but they are absolute monsters. They're huge, they're slow, and they guzzle power like there's no tomorrow. Then, on the other side, you have real-world apps. The stuff on your phone. They need to be lightning fast, super efficient, and use as little memory as possible. Because, let's be real, you can't exactly fit a whole data center in your pocket. That's the AI size problem in a nutshell. So how do you cram the power of one of those giant models into a tiny package? Well, the first big idea was to have the small model learn from a master. And they use this really powerful teacher-student analogy to do it. The method is called knowledge distillation, and it's pretty much what it sounds like. Imagine you've got this huge, wise teacher network that's already an expert at some task. Then we create a much smaller student network. The goal? It's simple. The student's only job is to learn how to produce the exact same final answers as the teacher. It's kind of like the student is just trying to copy the teacher's answers on a test without really understanding how they got there. And the process itself is pretty straightforward. Step 1, you train your big teacher network until it's an expert. Step 2, you train the smaller student network with one single goal in mind. Make your final answer match the teacher's final answer. Now this works, it's effective, but it's also pretty limited. The student is only learning the what, not the how. And this is where things get really, really cool. This is the breakthrough idea behind Fitnets. The researchers basically asked this brilliant question. What if the teacher could do more than just give out the final answer? What if they could give the student a little help along the way? And there it is. That's the core concept. Instead of just looking at the final output of the teacher network, the student gets a hint from one of the teacher's middle layers. All of a sudden, the student isn't just learning the final answer anymore, it's learning to copy the teacher's problem-solving process partway through. It's about learning the method, not just the final result. So this leads to a much more elegant two-stage training process. In stage 1, and this is the completely new part, the student network only focuses on its middle layers. It's trained to match that hint from the teacher's middle layers. This is all about learning the how. And only after it's got that down, we move to stage 2, where the whole student network gets trained using that traditional knowledge distillation to really refine the what. But wait, the cleverness here doesn't stop with just the training method. It's also got to do with the actual architecture of the student network. See, it's not just a shrunken down version of the teacher, it has a completely different shape. And this just lays out the difference perfectly. A traditional teacher network is usually what we'd call wide and relatively shallow. It has a ton of parameters. You can think of those as the little knobs the AI can tune to learn, all crammed into each layer. A Fitnet, on the other hand, is designed to be thin and deep. It has fewer parameters in each layer, but it has way more layers stacked on top of each other. It's just a fundamentally more efficient design for learning. This quote from the paper really gets to the heart of why this works so well. Being deep lets the network learn incredibly efficiently. Think of it like this. The first few layers learn really simple things, like edges and colors. Then, the next layers can reuse those features to learn more complex things, like shapes. And the layers after that combine those shapes to recognize actual objects. That depth allows the AI to build up really complex knowledge from very simple building blocks. So, okay, we've got a new training method, we've got a new architecture. The theory all sounds great, but does it actually work in the real world? Well, let me tell you, this is where the results get, honestly, they're kind of mind-blowing. So let's start with size. In their main experiment on the CAFAR-10 dataset, the student Fitnet had almost 10.5 times fewer parameters than its teacher. Just let that sink in for a second. That is an order of magnitude smaller and less complex. It's a huge leap in efficiency. All right, now for the big reveal. You'd expect a model that's 10 times smaller to be less accurate, right? I mean, that just makes sense. But the results showed the complete opposite. The big teacher network, it got an accuracy of 90.18%. The tiny little Fitnet student, it scored 91.06%. It wasn't just smaller and more efficient. It was actually smarter. This table just lays it all out, plain and simple. Compared to its teacher, the Fitnet is more accurate, has over 10 times fewer parameters, and as a result, it's over 4.5 times faster at making predictions. It wins on every single metric. More accurate, drastically smaller, and way faster. That is a clean sweep. Just incredible. Okay, so let's tie this all together really quick. The big problem was that our most powerful AI models were just too big and slow for practical use. The old solution, knowledge distillation, was basically like copying the teacher's final answers. Fitnet's huge idea was to add a hint from the teacher's thought process and use a new thin and deep shape. And the mind-blowing result? A student that can be smaller, faster, and even smarter than its teacher. And that really brings us to the big so what question. This isn't just some academic exercise. If we can pack more intelligence into smaller, faster, more efficient packages, what does that unlock for us? It means more powerful AI on your phone without killing the battery. It means smarter features in your car that can react in an instant. It means advanced intelligence in all sorts of devices in your home. This whole thing challenges the idea that bigger is always better, and it opens up a future where the smartest AI might just be the one you barely even notice is there.